Now we will start with our first speaker, Jude. Justin is doing his PhD under the supervision of Matthias Henning and Arno Onken at the Institute of Adaptive and Neural Computation at the University of Edinburgh. His research focuses on the intersections of neuroscience and the deep learning. Today, he will talk about the similarities between hippocampus and recurrent neural networks. His talk is titled Hippocampal Representations Emerge When Training Recurrent Neural Networks on a Memory-Dependent Maze in Navigation Task. Stage is yours, Justin.
Yeah, hi everyone. So today we're talking about how hippocampal representations and dynamics emerge when training a recurrent neural network on a maze navigation task. So recent work has shown the emergence of grid-like representations in the activation space of an RNN when trained on a velocity integration task, such as this work by Quavo and Wei. So they train on an agent in and its trajectories through a box, and then train an RNN on those trajectories, and then they see grid cells forming in the activation space. So we examined experimental results of training rodents on a T-shaped maze task. So in this experimental work by Johnson and Redish, a cue-tone is given to a mouse halfway up the maze stem, and this cue-tone modulates the reward location. So at the top of the maze, it has to choose to go left or right depending on the cue-tone given. And in this work, we use a modified form of this maze. So we tile the maze walls with randomly generated colors, and we first pre-train the agent to predict subsequent maze wall colors. And the cue-tone given halfway up the maze indicates the turn direction at the top of the maze. And the agent is not choosing its own actions here. It's just predicting subsequent wall colors. So through pre-training, we observed the formation of well-isolated place cells in several RNN units, as seen in the top row of unit activity here. For the activity figures in the bottom row, we run the agent from the bottom of the maze to the top of the maze stem and leave the agent stationary here for several time steps to simulate rodent pausing in an experimental setting. We observe that many units fire outside of their respective place fields, particularly at cue and at choice points. This is seen experimentally in rodents with substantial extra field firing of place cells at the maze choice point. So here we see 3 place cells with their place fields outlined, and then we see that these place cells are firing at the maze choice point here and here, which is denoted as extra field firing. So we extend the wall color prediction task to include navigation towards reward locations and solve this task using cue-learning. We train the RNN using a joint loss function of subsequent wall color prediction and of cue value prediction to maintain spatial localization ability. In addition, we train a single layered network to predict the agent's subsequent location based on the RNN's current activations. So after cue-learning, we also observe extra field firing, now in a greater range of RNN units throughout several maze locations. So again, we're seeing extra field firing at the choice point and the cue point and many locations in between. We find that the RNN has a non-local forward-moving representation after pre-training, where the inferred agent location moves far ahead of the agent when paused at the decision point at the top of the maze. So we see that the inferred location first follows the mouse, and then when it's paused, the inferred location moves all the way around the maze back to the start point. So after cue-learning, we note that the representation again moves forward and the agent is stopped at the decision point, but now also sweeps and switches arms. So first it goes down the reward path, switches to the non-rewarding path, and then goes back to the start, and then comes back down the rewarding side, and then rests at the end, at the start point of the maze. So this is mirrored in experimental results and may indicate active trajectory planning by rodents. Looking at a non-linear dimension reduced manifold of RNN activity over time shows how the forward sweeping representation switches trajectory twice before returning to the start location. So if we see the light blue trajectory starting with the left trajectory and then switching to the right trajectory and then coming back to the left trajectory, that sort of shows how the RNN activations change over time. And in addition, we note that place fields of RNN units drift forward towards reward locations throughout training. And this is shown experimentally by Lee et al. So their rewarding location is at the top of the central stem. So we see place fields moving towards this location in the central stem. And this is what we show in our results as well. Furthermore, we see that a higher proportion of RNN units are task phase selective than our trajectory direction selective. And this is also mirrored by Griffin et al. Experimentally. So in summary, we show that an RNN trained on a goal-based reward task in a T-shaped maze exhibits functional dynamics coinciding with hippocampal neurons, namely CA3 region neurons. Extrafield firing and non-local activity of RNN units emerges when an agent pauses at decision points, and that place fields drift towards reward locations throughout training. In addition, we show that far more RNN units are task phase selective than are trajectory selective, coinciding with CA1 region neurons in the hippocampus. Thank you. Shall I stop the share? Or?
Thank you, Justin. If you have any questions, please use question and answer panel at the bottom to ask your questions. While we are waiting for other questions, Justin, I have a question for you.
Yeah.
You are using Q-learning model.
Yeah.
I mean, for these animals, because as far as I know, the Q-learning is good when the animals are training, but when they know the task, it's slightly less compared to Bayesian or some model-based models. Mm-hmm. It is much more effective. And these animals, I mean, what is the training stage for them? Are they just learning the task, or do you see what I mean? What do you think it will happen if we compare it with the Bayesian or model-based learnings?
Oh yeah, so in this scenario, I guess it does learn the task perfectly, whereas the rodents only learn it about 60% effectively. So it's obviously not like completely biologically plausible, but we're looking at possibly extending to using model-based reinforcement learning. But that's a bit sketchy at the moment. Like, it's very recent work that's shown model-based reinforcement learning even works effectively. But yeah, as far as reinforcement learning goes, there's not much has changed since Q-learning in general, right? So there's not many options for this at the moment. But we're just looking at trying to marry the two together.
That looks good. And we have a couple of questions for you. Jeremy Forrest is asking, can you go into more details on your RNN, like number of units, LR? Could you please just explore your RNN a little bit more? Oh
yeah, so it's an LSTM with 380 units, and the learning rate we use is 0.0005. So half as slow as as people would normally go for, probably because at too fast a learning rate, it doesn't learn the intricacies of. So we're trying to do a joint loss function of both the wall color and the Q values. So a lower learning rate allows the agent to, or allows the RNN to integrate both of those pieces of information into its planning.
Sounds good. And we have another questions for you from Raunak Basu. He asking for are the extra field representation sequential?
What is he? I don't think I know what he means by sequential.
Yeah, Raunak, could you please clarify your questions in the chat or the panels? Then we can ask for it again. I can move on to the next questions while he's clarifying the question.
He said like theta sequences. So I'm not a neuroscientist, so I'm not exactly sure what theta sequences are. Yeah, I don't know what theta sequences are. I'm not going to lie. But I can answer this later on. I can talk to my supervisor about it and answer it later on if that helps.
Okay, thank you. And another questions from Eleanor Duval. Do you expect the splitter representations to occur in your model if both sides were equally rewarded? In other words, is the splitter effect depending on choice or future reward?
Splitter representation.
Because you have two options.
Yeah.
Do you think it is because of the choice, or is it because of the outcome they are receiving?
Oh, right. So they are equally rewarded, and in other words, depending on choice or future reward. So RL is based on future reward. So it's depending on choice. I'm not sure what she means actually by depending on choice or future reward. I'm not sure what she means by splitter effect either. Does she mean the forward moving representation? Oh, she means the LSTM dynamics. I think it's based on let's say the rat was just doing a future free choice in the maze.
If the rat has more choices instead of 2, what did you expect?
Oh, probably. Yeah, it's a good question. I'm not sure actually how it would work with more choice. Different place fields for the center left compared to the center right.
Eleanor is basically in the chat saying that, let's say the rat was just doing a free choice in the maze.
Yeah.
By splitter effect, Eleanor mean the different place fields for center left compared to center right.
Okay. What does she mean by center left? Sorry, I don't know what these phrases mean. So I think so. Well, with the UMAP manifold, that sort of behavior probably comes about because of the secondary cue, in the kind of schematic. Like, if the agent is expecting a secondary cue, it doesn't get it, then it will kind of switch to the opposite trajectory.
For example, Raunak is extending Eleanor's questions, saying that or place cells in the center arm firing at different rates for the 2 different choices. Currently, you have 2 actions, left and right, embodied actions, which is the choice. And they are basically, as far as I see, they're asking if that is not the embodied choices, actions, what would happen? Because the place cells will fire differently and
so the place fields form in the pre-training, right? And in that scenario, it has no choice over its actions. And I suppose, well, I don't actually show, so there are no place fields in the center arm, like well, in the example I showed at least, there weren't place fields in the center arm, but they're firing the place fields, the place cells that have place fields around the rest of the maze are firing in the central arm. And the place fields that we find first are averaged over both a left and a right run, and the actual firing is just on a left run, but it doesn't go the whole left way. It just gets the left sided cue and then stops at the top and then stays there for a while, and that generates activity in the central arm by RNN units that don't fire there normally, if that makes sense.
Eleanor and Raunak, you are very welcome to join our video and discuss it with Justin after Philip's talk, because we have extra 15 minutes. If you would like to be in the video, we can just, we are inviting you to come here and then ask your questions and then make a clear conversations with Justin if you like. Because Eleanor is extending the questions.
I don't know, splitter cells.
It might
we
be.
do find some trajectory dependent cells later on, but I don't necessarily, for the place field plots, I don't say whether they are trajectory dependent cells at all. But I think some of them, well, because of the extra field firing on a left field trajectory, some of them might be trajectory dependent, but I haven't kind of separated them as such. Yeah, sorry about that.
Yeah, thank you very much, Justin. Now it is time to move to the Philip.